There is a particular building on the outskirts of Hiroshima, set back from the road and surrounded by a perimeter of low, unremarkable hedges, where the sound of an internal combustion engine has been heard almost continuously for the past 60 years. The building belongs to Mazda. The engines being tested inside it, on most days, are conventional four-cylinder units, the kind that power the millions of vehicles the company sells annually across global markets. But on certain days, less frequently than the engineers there might prefer and more frequently than the company's public statements would suggest, the sound changes. It becomes higher, thinner, more continuous in its register, lacking the rhythmic punctuation of pistons rising and falling. It is the sound of a rotary engine, and for anyone who has spent time around these machines, it is unmistakable. What makes this sound particularly significant in 2026 is what has happened to the technology inside that building. Mazda has not merely preserved the rotary engine as a museum piece or a nostalgic artifact. The company has fundamentally reimagined it. Experts around the world are now saying that Mazda has not just brought back the old rotary engine, it has fully upgraded it and given it a completely new identity. The engine that now emerges from those testing facilities carries direct injection technology, a completely redesigned thermal management system with new cooling jackets and improved airflow architecture, diamond-like carbon DLC coatings on moving surfaces to reduce friction, advanced sealing technology that addresses the historic weaknesses of apex seals, and an intelligent ECU that constantly monitors and adapts the fuel-air mixture for optimal performance across varying conditions. This is no longer the unreliable, fuel-hungry rotary of the past century. It is a smart, efficient, and remarkably compact power unit, so small that it can easily be fitted alongside a battery pack and electric motor without consuming the kind of space that a conventional piston engine would require. The fact that this sound continues to be produced in 2026 in a small testing facility belonging to a company that publicly committed to electrification years ago is one of the more curious technical persistences in the modern automotive industry. But the story has evolved in ways that go beyond mere persistence. It is also the seed from which a particular kind of online speculation has grown and a new kind of strategic thinking that industry analysts say could reshape the competitive landscape. That speculation, in its most amplified form, suggests that Mazda is preparing to release a new rotary engine of such revolutionary efficiency and capability that it will fundamentally undermine the case for battery electric vehicles. The claim is large. Some industry estimates suggest that if Mazda pushes this technology fast, its market share could grow from approximately 2% to around 4 to 5% within just 2 years. Other major manufacturers, including some with dominant positions in the EV market like BYD and Hyundai, are reportedly studying similar range extender architectures in response to Mazda's move. The question being asked in boardrooms from Stuttgart to Detroit is no longer whether the rotary has a future, it is whether this particular implementation of the rotary as generator represents a new strategic race. Entirely. Experts have begun saying that Mazda did not join the EV race, it started a completely new race. But to evaluate these claims properly, they must be understood in the precise technical context in which they have emerged. The rotary engine, as it exists in automotive applications, is not a Mazda invention. It was conceived by Felix Wankel, a German engineer of considerable mechanical imagination and somewhat troubled biography, who began working on the concept in the 1920s and produced the first functional prototype in 1957 at the NSU Motoren Work Factory in Neckarsulm. The engine he designed dispensed with the reciprocating piston entirely. In its place sat a roughly triangular rotor, turning eccentrically inside a peanut-shaped housing, performing the 4 phases of the combustion cycle: intake, compression, ignition, and exhaust, simultaneously rather than sequentially. The mechanical elegance of this arrangement was immediately apparent to anyone who looked at it carefully. There were almost no parts. There was no valve train. There were no connecting rods, no crankshaft journals carrying alternating loads, no inertial penalties from masses being accelerated and decelerated thousands of times per minute. The engine was, in pure mechanical terms, a simpler object than the conventional reciprocating engine it proposed to replace, and it produced power with a smoothness that even its harshest critics conceded was remarkable. NSU licensed the design to manufacturers around the world during the 1960s, and most of them attempted prototypes. Mercedes-Benz built a rotary-powered concept car called the C111 that achieved speeds above 300 kilometers per hour in development testing. General Motors invested significantly in rotary research and built running prototypes intended for production vehicles. Citroën produced a small number of rotary-powered cars before quietly withdrawing from the technology. By the early 1970s, almost every major automaker concluded that the rotary engine, despite its mechanical elegance, suffered from a set of problems that conventional engineering could not adequately solve. The seals at the tips of the rotor, which had to maintain contact with the housing across millions of cycles at high temperatures, wore unevenly and failed prematurely. The shape of the combustion chamber, elongated and constantly moving, made it impossible to achieve the kind of efficient flame propagation that piston engines produced in their nearly spherical chambers. Fuel consumption was poor. Emissions, particularly hydrocarbons from incompletely burned fuel passing through the long combustion chamber, were difficult to control. By 1975, every major manufacturer that had licensed the technology had abandoned it. Every manufacturer except one. Mazda, then a relatively small Japanese company called Toyo Kogyo, made a decision that the larger automakers considered eccentric. It would not abandon the rotary engine, it would persist with it. Specifically, it would continue refining the technology in the belief that the problems other engineers had judged insurmountable were in fact solvable through patient, incremental engineering. The decision was driven partly by the personal commitment of the company's leadership, partly by the absence of alternative differentiating technologies that a small manufacturer could plausibly develop, and partly by a kind of corporate stubbornness that, viewed in retrospect, looks something like vision. The engineers assigned to the rotary program at Mazda spent the next 4 decades working on the same fundamental problems that had defeated everyone else: tip seal durability, combustion efficiency, fuel economy, and emissions. They achieved meaningful progress on all of them, though never quite enough to make the rotary engine competitive with conventional powertrains across the full range of automotive applications. The result of that persistence was a series of cars, the RX-7 and RX-8 most prominently, that built a particular kind of cult following. Owners of these cars were willing to accept the rotary engine's compromises, its thirst for fuel, its appetite for oil, its unconventional service requirements, in exchange for the smoothness and the high-revving character that no piston engine could match. The cars sold in modest numbers and lost money for the company on a per-unit basis, but they sustained the engineering knowledge base. They kept the rotary alive. When Mazda finally discontinued the RX-8 inches 2012, the rotary engine left mainstream production for the first time in over 40 years, and most automotive journalists wrote what amounted to its obituary. The engine had been a noble technological detour. It had produced some memorable cars. It was now finished. That conclusion turned out to be premature. In the years following the RX-8's discontinuation, a small team within Mazda continued working on rotary technology, but their objective shifted. They were no longer trying to build an engine that would propel a car directly through its drivetrain. They were trying to build an engine that would generate electricity. The distinction is more consequential than it might initially appear. What has emerged from this decades-long research program is a new generation of rotary technology that addresses the historic weaknesses with remarkable thoroughness. The direct injection system solves the fuel control problems that plagued earlier designs by delivering fuel precisely where it is needed in the combustion chamber, improving both power output and fuel economy. The redesigned thermal management architecture, featuring new cooling jackets and optimized airflow pathways, addresses the overheating issues that historically limited the engine's performance and durability. The DLC coatings on internal surfaces dramatically reduce friction and wear, extending component life while improving efficiency. The advanced sealing technology, the solution to the problem that defeated every other manufacturer, uses improved materials and geometries to maintain the critical seals at the rotor tips far more reliably than any previous implementation. And the intelligent ECU continuously monitors engine conditions, adjusting fuel delivery, ignition timing, and other parameters in real time to maintain optimal operation across all conditions. When a rotary engine drives the wheels of a vehicle directly, it must operate across an enormous range of speeds and loads, idling at traffic lights, accelerating through gear changes, holding steady at highway speeds, climbing grades, decelerating into corners. The fundamental inefficiencies of the rotary architecture, particularly its poor combustion efficiency at low loads and partial throttle openings, are exposed across this entire operating envelope. But when a rotary engine functions purely as a generator, charging a battery that then drives an electric motor, those inefficiencies become avoidable. The engine can be operated at a single, optimized speed in a single load condition in the precise narrow band where its thermal efficiency reaches its highest achievable value. The compromises that ruined it as a primary powertrain become, in this configuration, much less significant. This is why the rotary's compact size becomes so strategically important. It can be integrated into vehicles without the packaging penalties of larger conventional engines, freeing interior space or allowing larger battery packs. The MX-30R EV, which Mazda introduced to European markets in 2023 and has progressively refined since, uses a small single-rotor Wankel engine of approximately 830 cubic centimeters displacement to generate electricity for a battery pack that drives an electric motor producing about 168 horsepower at the wheels. The car is a series hybrid in the strictest sense. The rotary engine never directly powers the wheels. It exists solely to extend the vehicle's electric range when the battery is depleted, allowing a car that would otherwise be a pure battery electric vehicle with a relatively modest 3-5-mile electric-only range to travel an additional 350 miles or so on a tank of gasoline. This is not a revolutionary technology in the sense of reinventing physics, but it is a thoughtfully executed range extender, and its significance becomes clearer when one considers the practical limitations that pure electric vehicles still face in real-world conditions. The driving experience this system delivers is, by all accounts, remarkably different from what the rotary's historical reputation would suggest. The transition between battery power and generator operation is seamless and almost undetectable to the driver. The cabin remains quiet. The acceleration feels electric, immediate, smooth, free of the vibration and interruption that characterize conventional engine starts. This is what Mazda means when it speaks of zero charging anxiety. The driver gets all the benefits of electric propulsion, the silence, the torque, the smoothness, without the need to plan routes around charging infrastructure or wait for extended periods while the battery replenishes. Fill the tank, keep driving. The system can reportedly achieve ranges of 800 to 1,000 kilometers without external charging, effectively doubling what a conventional electric vehicle can manage on a single charge. This technological configuration is not merely an engineering exercise, it is also a strategic response to the charging infrastructure gap that continues to constrain EV adoption in many markets. In markets where charging stations remain sparse, where distances between population centers are large, and where the behaviors of rural and developing market consumers differ from those of urban early adopters, a series hybrid configuration with a small, efficient generator and a modest battery, offers something that pure battery electric vehicles cannot. It offers freedom from charging anxiety without the weight, cost, or material intensity of a full-size battery pack. And the rotary engine, in this configuration, has specific advantages over the piston engines that other manufacturers have used in similar range extender applications. It is smaller and lighter for a given power output. It produces less vibration, which matters when the engine is running while the vehicle is otherwise being driven on electric power. It has fewer moving parts, which simplifies packaging and potentially reduces long-term maintenance costs. It can run on multiple fuel types, including synthetic fuels, and in future iterations, hydrogen, a capability that positions it well for a world where the energy transition proceeds along multiple pathways rather than a single dominant one. Mazda's ambitions for this technology extend well beyond a single model. Within the next 2 to 3 years, the company plans to deploy the rotary range extender system in its SUV lineup, beginning with the CX-60 and CX-90. The strategic logic is straightforward. These are the vehicles where packaging space is most critical, where customers most need extended range without the burden of frequent charging stops, and where the weight and volume advantages of the compact rotary generator are most pronounced. Beyond that horizon, Mazda's stated vision for 2030 is to make its entire vehicle lineup multi-energy compatible, a fleet that can accommodate pure electric vehicles, conventional hybrids, plug-in hybrids, and range extender models using the rotary generator technology depending on the requirements of specific markets and customer segments. The patent filings that have emerged from Mazda over the past several years tell a more nuanced story than the market share projections might suggest. The company has filed intellectual property claims related to multi-rotor configurations, hydrogen combustion in rotary engines, improvements to apex seal materials, and integration of rotary generators with various battery chemistries. Some of these patents reflect genuine technical advances. The work on hydrogen combustion is particularly interesting because the rotary engine's inherently separated intake and combustion regions, which were a liability in conventional gasoline applications, become an advantage when running hydrogen, which has a much higher auto-ignition tendency than gasoline and benefits from the thermal separation the rotary architecture naturally provides. There are credible engineers who believe that a hydrogen-fueled rotary range extender could play a meaningful role in the heavy-duty transportation sector, where battery-only solutions face fundamental scaling challenges, but this is a long way from destroying the electric vehicle industry. It is, at most, a complementary technology that addresses a specific subset of mobility needs that pure battery solutions handle poorly. The numbers, when examined honestly, do not support the more sensational framing. The rotary range extender in the MX-30 REV achieves a thermal efficiency of approximately 40% under optimized conditions, which is competitive with modern piston engines but not transformatively superior to them. Toyota's Atkinson cycle hybrid engines achieve similar or marginally better thermal efficiencies in similar applications. The total system efficiency of a series hybrid is constrained by the multiple energy conversion steps involved: chemical to mechanical in the engine, mechanical to electrical in the generator, electrical to chemical in the battery, chemical to electrical out of the battery, electrical to mechanical at the drive motor. Each conversion involves losses. The cumulative effect is that a series hybrid, no matter how clever the engine generating its electricity, cannot match the efficiency of either a pure battery electric vehicle running on grid electricity or a parallel hybrid that allows direct mechanical drive in appropriate conditions. The rotary engine does not change this fundamental thermodynamic reality, however much its new technologies have improved its underlying performance. What Mazda is actually doing, when its work is examined without the distorting filter of speculation, is something more measured and more interesting than the destruction of an industry. It is preserving optionality. The company has committed to electrification, and its product roadmap includes battery electric vehicles that will compete in mainstream segments. But it has also recognized that the path to full electrification is neither uniform nor inevitable, that different markets will electrify at different rates, that hydrogen may yet find applications in segments where batteries struggle, and that having a sophisticated, refined rotary generator technology in its portfolio gives it the flexibility to address scenarios that pure battery commitment forecloses. The industry response, the attention being paid by competitors, the investor movement into Japanese auto stocks, the strategic reassessment happening in boardrooms suggests that this is not merely internal reasoning. Others see the same optionality value. This is not bombshell strategy. It is hedged industrial reasoning of the kind that companies with long memories tend to practice, and Mazda, having survived its own near destruction in the early 1970s by refusing to abandon an unconventional technology, has perhaps more institutional reason than most to value optionality. The rotary engine, after all, has been the company's point of differentiation for over half a century. It has defined Mazda in the eyes of enthusiasts, shaped its brand identity, and given it a technical story that no other manufacturer can replicate. Abandoning it entirely would have been the logical choice by any conventional measure, and it would have left Mazda as just another mid-sized automaker competing on the same terms as everyone else. Preserving it, even as a niche generator in a range extender application, keeps that identity alive. The persistence of the rotary engine inside Mazda's research operations, then, is best understood not as a threat to electrification, but as an expression of a particular philosophy about how technological transitions actually unfold. The engineers in Hiroshima who continue refining the apex seals of a Wankel rotor in 2026 are not preparing to overthrow the electric vehicle industry. They are preparing for a future in which multiple powertrain technologies coexist, in which the answer to the question of how to move people and goods from place to place is more complex than any single technology has the capacity to provide, and in which a small, efficient, vibration-free generator capable of running on hydrogen or synthetic fuels might find applications that the engineers themselves cannot yet fully predict. That future may arrive sooner than the thermodynamics alone would suggest, particularly if charging infrastructure continues to lag behind vehicle deployment, particularly if hydrogen infrastructure develops in the ways that some projections anticipate, and particularly if consumers in large and growing markets demonstrate the same preference for practical flexibility over ideological purity that they have shown in virtually every previous automotive transition. When Mazda introduced its Rotary Plus hybrid range extender system, it did not just show a new technology, it raised questions about the prevailing model. If a car can drive completely like an electric vehicle, silent, smooth, with immediate torque, but keeps running without the need to stop for extended charging sessions, then the calculus that makes pure EVs attractive shifts. People will naturally ask what the additional cost and limitation of a pure battery vehicle buys them when a more flexible alternative exists. That is the question Mazda has opened, and it is a more interesting and consequential question than any claim about destroying an industry. The sound that continues to emerge from that building on the outskirts of Hiroshima, then, is not the sound of an industry being destroyed. It is the sound of a technology being kept alive by a company that has learned, through a long and at times painful institutional history, that abandoning a difficult engineering problem too early is a mistake more frequently made than the opposite. Whether the rotary engine eventually finds the broader application that Mazda's continued investment and expanding strategic ambitions imply it might, or whether it remains a niche solution in a small number of specialized vehicles, is a question that will be answered by markets and physics and the unpredictable trajectories of fuel infrastructure over the coming decades. The answer will not be that the rotary engine destroyed the electric vehicle industry. It will be something less dramatic and more interesting, that engineering, when practiced with patience and without the demand for revolutionary outcomes, has a way of producing useful results in places where the more confident predictions of disruption rarely look. And in the meantime, the engineers in Hiroshima will keep listening to the sound of that rotor turning and adjusting and improving one iteration at a time.